Hello everyone, today I'd like to demonstrate several RF instruments that are commonly used in antenna and wireless communication measurements. In this demonstration, I'll be using three important pieces of equipment: vector network analyzer, RF signal generator, and also spectrum analyzer. I'll start with the vector network analyzer. Before connecting the antenna, the VNA must first be calibrated. Calibration removes the effect of RF cable and connectors so that the measurement represents only the antenna itself. Without calibration, the measure S11 could include unwanted errors from the measurement setup. After calibration, the antenna is connected to port number 1 of the VNA. The parameter I'm interested is S11, also known as the reflection coefficient. S11 tells us how much of the transmitted RF power is reflected back toward the source. If the antenna is well matched to the transmission line, very little power is reflected and most of the power is radiated. From the measurement, the antenna resonates at several frequencies: 761 MHz, 1.299 GHz, 2.223 GHz, 2.369 GHz, 2.515 GHz, and 2.741 GHz. These resonant frequencies indicate the operating bands of the antenna. Since the return loss at this point is below -10 dB, the antenna has acceptable impedance matching for practical RF applications. Once the antenna characteristics have been verified using the VNA, I can now evaluate how the antenna performs in actual wireless transmission setup. Here, I'm using a Cordon-Schwarz RF signal generator. The generator produces continuous RF signal at 2.3 GHz, which is one of the operating frequencies obtained from the VNA measurement. During the demonstration, I varied the output power between -20 dBm, -5 dBm, and 0 dBm. Observe how the received signal change. Instead of connecting the instrument directly using cable, the RF signal is transmitted over the air using two antennas. The transmitting and receiving antennas are separated by approximately 1.5 meters. The distance helps ensure that the antenna operate within the far-field region, where the electromagnetic wave behave much more closer to a plane wave. Measuring in the far field provide a more realistic representation of actual wireless communication than measurement taken in near field. The receiving antenna is connected to a keysight spectrum analyzer. Unlike an oscilloscope, which displays voltage versus time, a spectrum analyzer displays signal power versus frequency, and this allows us to identify the transmitted frequency and measure its received power level. The first transmission is performed with the signal generator output set to -20 dBm. On the spectrum analyzer, the received signal appears exactly as 2.3 GHz, while the measured power is approximately -44.97 dBm. Next, the generator output is increased to -5 dBm. The received signal strength increases to approximately -26.54 dBm, while the frequency remains unchanged. And finally, the generator output is increased to 10 dBm. The received signal is measured at approximately -23.99 dBm. As expected, increasing the transmitted power results in a stronger received signal. However, the received power is still lower than the transmitted power because RF signals experience attenuation during propagation. Additional losses are contributed by antenna efficiency, connector losses, stable attenuations, and free space path loss. Behavior is completely normal in particular RF communication systems. Together, these instruments form the foundation of antenna testing, wireless communication measurements, and RF system development, making them essential tools for RF and communication engineers. Thank you, that's all for me.